Okay, so let's get started. We were discussing about optimization over a convex set. The problem we are trying to solve is minimize f of x. X is in a convex set capital X, which is a subset of Rn, and it's a closed convex set. And we talked about various types of convex sets that we typically study in the context of optimization. And today, what we want to do is talk about necessary conditions for optimality. What happens if the function f is convex over this closed convex set? Then, of course, the necessary condition also becomes sufficient. So we'll talk about that, and then we'll get into the algorithmic development for the class of problems of this type. So let's say we are in a convex set. Let's say this is my convex set, and I'm standing at a point x, and I want to figure out what are the feasible directions at x, right? So when we were talking about unconstrained optimization, I could go in any direction, right? I'm not constrained by anything. Now we are in a constrained setting. I have to be within the convex set. So I want you to think a little bit about what would be my feasible directions. So what are the directions in which I can go, and what are the directions in which I cannot go? So, well, maybe I drew it in the middle so you can, it doesn't make any point. But if I'm here, then I have a direction D here and I have a direction D here. So which D is feasible and which is infeasible? Okay. So I think you got an idea that this direction D1 seems to be feasible, because if I take a small step in the direction D1, I'm still within the convex set, whereas this D2 is infeasible. So I'm standing at x. Even if I take a small step in the direction D2, I'm outside the set, and therefore I'm infeasible. How do I write this mathematically? How do I say that D1 is feasible and D2 is infeasible? Well, the way to say that is I have x. I am at a point x in capital X. Then I pick another point y in capital X. Then y minus x is a feasible direction. And if alpha is your step size, typically between 0 and 1, right? Then your x plus alpha y minus x is the new point. Okay, so I'm standing at x, I'll pick another point y, which is in the set capital X, which is in the convex set capital X. Then y minus x is a feasible direction because I can move in that particular direction. By convexity, if you're standing at x and you're moving in this direction, let me call this D. If you're moving in this direction, as long as your step size is less than equal to 1, you will always remain within the set. Okay, that's by definition of convexity. Alpha is the step size, so this is the new point. And hopefully, if alpha is less than equal to 1, then x plus alpha y minus x is also in capital X. And the way to see it is, you break this down, this is alpha y plus 1 minus alpha x, right? And this is, by definition of convexity, y is in x, x is in x. So this point must be in capital X, just by definition of convexity. Okay, this is simple and straightforward. Let's talk about global and local minimums. So X star is a global minimum if and only if f of x star is less than f of x for all x in capital X x star local minimum if and only if f of x star is less than f of x for all x in capital X such that x minus x star is less than epsilon. So I need to add a small condition here. There exists epsilon greater than 0. Okay, so this is just mimicking the definition of unconstrained minimum which we had studied. The only difference is in the unconstrained minimum, x was equal to Rn, so we didn't care about feasible direction, but the definition of global and local minimum remains the same. Just replace x with Rn. On the other hand, when you are in a convex set setting, we have to maintain that constraint that for all x in capital X. So nothing complicated going on here. So what would be a necessary condition for optimality? So we just have to start with this definition, and this is the result. So X star local minimum implies gradient of fx star transpose x minus x star is greater than equal to 0 for all x in capital X. So gradient of fx star is a vector in n dimension. So I look at the gradient at x star and I transpose it with x minus x star for all x in capital X. And that should be greater than equal to 0. If this was a local maximum, all you have to do is make it less than equal to 0. But remember, we are not talking about local maximum in this course. So it should be greater than equal to 0 here. Okay, how do we prove this result? So what exactly is happening here? So I'm standing. So let's go back to this particular example. So I have a whole bunch of feasible directions. This is for general function, this would be a local minimum. But for convex function, that would become a global minimum. Okay, so if f is convex, then x star is a global minimum if and only if this condition holds.
So we don't need to perform constraint?
No, not really. The reason for that is, going back to this example, this is a epsilon ball around x star, right? But if you look at the feasible directions, all of the feasible directions, as long as your step size is sufficiently small, you are within the ball. right? So it doesn't matter whether you're considering a small ball or a big ball. It doesn't matter because the feasible directions doesn't change.
Because it's convex.
Yeah,
If
because
it
it's
was not
convex.
convex, it would be convex.
That's right. That's right. If it were non-convex, then this condition will not hold. Okay. So that's where convexity plays a big role in the class of algorithms that we will be studying. Yeah.
If it's not convex, can we add a second order to it to make it a...
Not really. Not really. So let's look at a non-convex set. I'm standing here at x star. This is my point y. So for some time, I'm within the set, but then I go outside the set. So yeah, I can't really make sense of this feasible direction stuff. By the way, the most interesting non-convex sets are not like this. Most interesting non-convex sets are essentially points in the space. Okay? And now you have to do optimization over points in the space. To give you an example of a non-convex set of this type, remember I was in GE research last week and I was presenting my paper. So another paper that was studying a very interesting problem, which is crew scheduling problem. It's called a crew scheduling problem. So remember, GE has wind farms all over the world, and GE does maintenance for those wind farms all over the world. So they have maybe like 400, 500 people across the world who are experts on wind farm maintenance. Okay, only they can touch a GE wind farm. You cannot go and touch GE wind farm. Now so if you have wind farm all over the world, you have to fly these 400 people out to maintain those wind farms, and there are many issues with those requirements. So for instance, person one doesn't have visa to go to country number two, so the wind farm in country number two cannot be maintained by person one. Person two wants to go on a vacation for x number of days or whatever, so he or she is not available to do wind farm maintenance in that particular day. So that's a crew scheduling problem. You add those constraints, and essentially it's a 0-1 variable, right? So either the person is going to be in Bulgaria to service the wind farms in Bulgaria, or the person is not going to be in Bulgaria to service. Sometimes there are also constraints like the wind farm can only be maintained by 3 people at a time, because you need another crew member for safety reasons. If somebody has to harness them or something if they are climbing up or climbing down the towers. So it's a very complicated problem. They had like some 7 million or 8 million variables, some obscene number of variables that they were trying to optimize. And that was a non-convex problem because it was a 0-1 problem. You can either have 0 or 1. You can't have anything in between. So that's an example of a non-convex problem that needs to be solved. And they saw, I don't know, 10-15% improvement in the total cost for servicing those wind farms. And remember, at G scale, those 10% cost is probably hundreds of millions of dollars. Okay, so these, you can really bring the cost by using the tools. I mean, of course, we are not talking about these problems, so we are not studying this in this class. But hopefully, if you can take some courses in ISE departments on optimization, non-convex optimization, you can try and solve these problems for whatever companies you go to, and you can save them $100 million, and then in turn, you can charge them $1 million for providing that service. So you can really make a lot of money out of this class. Okay, that's the nutshell, the message in a nutshell. So whatever I am teaching is going to make you a lot of money. So listen carefully. Anyways, short detour, but non-convex sets are of these type that are most interesting non-convex sets. But for now, we are focusing purely on convex sets. Right. So this is the thing. Now let's look at the example that we were looking at. So these are all the feasible direction. What this statement is saying is that the inner product between the gradient and all the feasible direction has to be greater than equal to 0. When are inner products between two vectors non-negative? When are inner product between two vectors equal to 0? When they are orthogonal. Okay, when they are orthogonal. So when are inner products between two vectors non-negative?
Yes.
when the angle between them is less than 90 degrees. So in this particular example, most likely the gradient of function at x star is going to be pointing in this direction, so that no matter which feasible direction I pick, my inner product is going to be non-negative because the angle between them is less than 90 degrees. In essence, your gradient of fx star will not be going outside the set. It will be pointing towards inside the set, not outside the set. So that's the most important outcome, the geometric outcome of this particular result. So let's look at proving this result. It's a very short proof. So I have f of x star plus alpha x minus x star minus f of x star is greater than or equal to 0. That comes from this definition. So I'm taking a step in the direction x minus x star. The step size is alpha. I'm assuming alpha is small. And I subtract from it minus fx star. It has to be non-negative because x star is a local minimum. So it satisfies this condition. Actually, it satisfies this condition also. So no matter which part you are looking at, global or local, it satisfies this condition for alpha sufficiently small. What's our favorite thing to do? So alpha is positive, alpha is greater than 0, alpha is small. What do we do whenever we see some difference of functions and we see alpha greater than 0? We divide it by alpha and we take the limit alpha goes to 0. Can someone tell me what this statement is? What is the function minus fx star divided by alpha as alpha goes to 0? It's exactly equal to gradient of fx star transpose x minus x star greater than or equal to 0. Okay, so that's the necessary conditions for optimality. Essentially the same proof is going to work for the function if f is convex. The only difference is in the convex function, so remember that in convex function we know that f of x plus t is always greater than or equal to f of x plus gradient fx transpose t. Okay, so use this fact and this result or this technique, and you get the result that f is convex, then this is also sufficient. X star global if and only if gradient fx star transpose x minus x star is greater than or equal to 0. Okay. Okay. So let's look at an example. Just to get our hands dirty, I'm looking at this example. We are not going to look at more examples of this. But what does it mean for? Remember, it's a necessary condition for optimality because we assume that X star is a local minimum to begin with, and then we prove what is the condition that X star is going to satisfy. It doesn't go in the reverse way, so it just allows you to do a sanity check whether a given X star is an optimal solution or not, but it doesn't give you any proof of certainty unless your function f is convex. So let's look at an example. We have orthant, positive orthant. So this is x greater than equal to 0. So we are looking at this region. And let's say I am at a point x star. Where should the gradient of function f be pointing towards in this case? So remember that the gradient is going to be looking inwards. So the gradient of the function has to be going into the set. But now it could go in this direction, it could go in this direction. All of these directions are possible. But if I say that this is a local minimum, where exactly would the gradient be pointing to? Anybody wants to take a guess? Yeah.
All the points.
So you are saying that it will be pointing in this direction? Okay, so one person is saying it should be pointing in this direction, right? Okay, so then a feasible direction is in this direction. It's making a negative inner product. So that's not feasible, okay? Because it says it has to make a non-negative inner product. Okay, so this is not possible. The gradient of function will not be pointing in this direction. Yeah. So it's pointing in this direction. I can create a feasible direction in this direction, and then it's making an angle greater than 90 degrees, and therefore that's violates the condition.
If the function we are looking at is convex and is to the pointing outwards.
Pointing outward, downward. Okay, if it is pointing thisward, then almost no matter which feasible vector you pick, it's going to be making a negative inner product.
And it will be
Upward, okay? So that's right. So gradient of the function f will be pointing upward. Okay, it will be pointing upward because no matter which feasible direction you pick, it's making a non-negative inner product because the angles between the two vectors is less than 90 degrees, or in some cases it's equal to 90 degrees if you're looking at it in this direction. Okay, so how do we prove this mathematically? So pictorially, this looks feasible. Let's try to prove it mathematically. So I want, let's say I'll make two claims. So xi star is greater than 0 or xi star is equal to 0. So there are two cases. So if xi star is greater than 0, so in this case, x1 star is greater than 0 and x2 star is equal to 0. So remember, this is the x2 direction. So x2 component is equal to 0, whereas x1 component is positive, right? So we are satisfying this condition here at this particular x star. So if xi star is greater than 0, I can pick one x as xi star, x star plus, let's not look at this example right now, plus alpha ei x star. And x star minus alpha ei By picking alpha sufficiently, remember what is EI? EI is a unit vector in the ith direction. So is this a feasible vector? By picking alpha sufficiently small, I can make sure that this is all the components are non-negative. By picking alpha sufficiently small, I can make sure that all components are non-negative in this case. So therefore, these x is greater than equal to 0, because that's the constraint here. That's the feasible direction. So what is gradient of f at x star transpose x minus x star? So this is gradient of fx transpose alpha times EI and gradient of fx star transpose negative alpha EI. Okay. So what is this inner product of this vector with EI? It's the gradient with respect to the ith dimension. So this is alpha del f over del xi evaluated at x star. This is alpha minus alpha del f over del xi evaluated at x star. Both of them have to be greater than equal to 0. Okay, so I have alpha, which is a positive number, multiplied by a derivative, and negative alpha multiplied by the same derivative. This derivative is the same. Both of them have to be non-negative according to this requirement. When can that happen? If the derivative itself is equal to 0. So this implies so if xi star is greater than 0, then the derivative has to be equal to 0. Okay, and that's what we are seeing here, that the derivative, if you look at the direction of the derivative, it has some component along x2 direction, but along x1 direction it has 0 component, right? It has no component. So the derivative with respect to x1 is 0, whereas derivative with respect to x2 would be positive. Okay.
We make the second line x equals x star plus alpha e such that like x star minus alpha e is possible.
Yeah, so by picking alpha sufficiently small, I can make sure that both of these are non-negative vectors. Only then they are feasible. So feasible vectors are x greater than equal to 0. Okay. Let's look at yeah.
Is this called interior point of the set or?
Not quite. We're not talking about interior point. So interior point would be something that's not on the boundary. So something here. But in a convex set setting, the notion of interior point is a bit complicated. So that's why I'm not introducing that in today's lecture. So remember that a convex set could be just like my hand is a convex set. Just if you look at my fingers, it's a convex set in the 3D space. Now, if you pick a point here, you definitely have an epsilon ball along my hand, but you can also have an epsilon ball that is protruding outwards from my hand and going downwards from my hand, and that's not part of the set. Okay, so interior actually doesn't exist in this case. However, what exists is known as relative interior. So this is relative with respect to the convex set, but we're not looking at vectors that are pointing outwards of the set itself. Okay, so that's why we don't want to get into that. Yeah.
Do we need to specify I equals to or?
No, this is xi star is greater than 0. So I already know which I am picking.
Oh.
Yeah. Okay. So xi star. So I'm looking at xi star, x star. So some components are greater than 0, some components are equal to 0. Right? Those are the only two options. I'm looking at the component that is strictly positive, and I'm looking at those EIs in this case. Now let's look at the other condition where xi star is equal to 0. If that is the case, then I can only pick this one. I cannot pick this one, because if I subtract anything from that location, then I'll get an infeasible vector. So then I have the same thing here. I'll look at gradient of fx star transpose x minus x star. I no longer have this term. I no longer have this term. And I have this is greater than equal to 0. And alpha is positive. So what I have is this is greater than equal to 0. Which is exactly what this figure is pointing to, that the gradient will have a positive or non-negative derivative along x2 star. Okay. So that's just the way, so what the math is saying and what the picture is saying, they have to agree, right? Because math is the ultimate truth. So that's what I wanted you to envision. So this is the picture you should always have in mind, that whenever you are standing at the optimal solution, your derivative should be pointing inwards towards the set. But then where exactly would the derivative be pointing depends on a lot of different factors. So there are many different sets in the book where they talk about what the derivative should be satisfying at different points given different sets, but we'll not go into all those different conditions. Okay, let's jump into any questions on this before we jump into algorithm. So now let's start doing algorithm design based on this stuff that we have studied. Okay. So let's go back to the convex set. So I have this convex set. I'm standing at this point x0. And I need to descend. I need to figure out to what direction should I descend, what is the direction I should take so that I reach x1 So what should my d0 be? So that if I pick a step size in that direction, remember what my ultimate goal is? My goal is that my fx1 should be less than fx0. Right? As long as x0 is not an optimal point, I want to descend. I want to get to a point where my function value is strictly lower. That's the ultimate goal in optimization. The only difference is I want my x1 to be in the set capital X. This was not the case in the unconstrained optimization. I could pick x1 anywhere in the space. Now I'm restricted to picking x1, which is within the set capital X. So what would you do? What would you do? No, line search is fine. Line search we will do for figuring out alpha naught, but first we need to figure out d naught. So for line search, you first have to have a line. Only then you can search what the best alpha is going to be. How do we pick d naught? Right. So remember that x1, what is the feasible direction? This is x minus x0. Right? Those are all the feasible directions. And I want to make sure that I minimize the function f. So what I want is gradient of fx naught transpose x minus x naught should be minimized. Okay, so I'm standing at x naught. I'm looking at this. I can compute the gradient of f at x naught. Okay, so that's something that's given to me. I have a program, I have a code that gives me the gradient. I'm going to look at all possible x minus x naught. I'm going to look at all possible x minus x naught because those are all the feasible directions. And I want to minimize this inner product in order to find my feasible direction. So let's say x star, x0 star is where this particular inner product is minimized. I'm going to pick my descent direction d to be x0 star minus x0. And I'm going to take a small step alpha. I'll pick a step size alpha and I'll take a step in that direction. And then I'll repeat this process all over again. Okay. When do I know I can terminate? When this inner product is non-negative in all the directions. So for all x in x, this particular inner product is non-negative. Then I know that I can terminate because I'm satisfying the necessary condition for optimality. Now, of course, that's not a guarantee that it's an optimal solution, but at least it's a good candidate optimal solution. Okay, so at every point of time, I'm going to find the descent direction by solving a problem where I'm trying to minimize an inner product of this type, and then I'll take a descent. I'll take a step in that direction. So typically speaking, we are looking for xk star such that gradient fxk transpose xk star minus xk is less than equal to 0. Because if it is greater than equal to 0 for all x in x, then it satisfies the necessary condition. So we are looking for xk star such that this condition is satisfied. And then my descent direction dk xk star minus xk. Actually, this should be strictly less than 0. Then how do we pick alpha? So suppose we have figured out the descent direction dk. How do we pick alpha? So there are many methods to do that. So how to pick alpha k? So one is limited minimization rule. So you have alpha k equals to argmin alpha in 0, 1. Okay, so there are many ways to pick alpha k. I've listed 3 because 3 comes from the book. but you really can pick a diminishing step size, or you can come up with your own step size selection rule, as long as your alpha k is either equal to 1 or alpha k is less than 1. Because remember, if you pick alpha k greater than 1, you might get into the infeasible region. So we don't want to pick alpha k greater than 1. So as long as we pick alpha k something that is 1 or less than 1, we are in good shape. Okay. So that brings me to the first algorithm, which is known as conditional gradient method. We are just going to mix the two things that we just discussed, and we design an algorithm called conditional. I don't like these chalks. It's very painful to write. Conditional gradient. They have made these chalks too soft.
So we need to have a constraint here, but for the between
Alpha between 0 and 1.
what if, like for alpha equals 0.8, maybe like x plus alpha dk is out of the, on x set?
No, it cannot be, right? Because dk is always something which is x minus x naught, right? So you are always going to be within the set, yeah, because of this. Okay. So conditional gradient method says I'm going to pick x bar k to be the argmin of gradient fxk transpose x minus xk. This x is in capital X, and then my xk plus 1 is equal to xk plus alpha k x bar k minus xk. This is my dk. So I have two questions for you. This is conditional gradient method. Why does it make sense and why doesn't it make sense? Okay, so why does it make sense to solve this problem, and why doesn't it make sense to solve this problem? Okay, so let me give you a hint. I'm trying to solve this problem, which is optimization over a convex set, and I'm solving a problem which is optimization over a convex set. Okay, so I started with so I told you, so I'm cheating in some sense. I told you that I'll teach you how to optimize over a convex set, and now I'm cheating you again by saying that in order to find the descent direction, you have to do optimization over a convex set.
But that's a simple problem in that we have, like, instead of looking at f, we are looking at.
That's right.
So is that
correct? So it's not cheating.
Easier.
Yeah, exactly. So I'm not really cheating. So he's right, because remember, originally I was trying to solve a complicated nonlinear function f of x over the convex set, but now I'm saying that I'm only looking at the gradient transpose x minus xk, and I'm solving a simpler problem over a convex set rather than a complicated problem over a convex set. And as it will be clear to you over the course of this class, that solving linear problem over a convex set is much easier than solving complicated nonlinear optimization problem over a convex set. Okay. One more thing you will notice is I can really write this problem. So remember, there are two terms here, right? Gradient of fxk transpose x minus gradient of fxk transpose xk. But you would notice that the second term actually doesn't depend on x. It's just a constant, right? So I can just change this, replace this with gradient fxk transpose x and minus some constant. But remember, we want to know what the argument is. We don't care about the value. So whatever constant is getting added to the objective function, we don't care about it, because the argument is not changed by adding a constant to a function. Only the function value, only the value gets changed, but the argument doesn't get changed. X star still remains the same. This is also known as a Frank-Wolf method. So some people call it conditional gradient method, some people call it Frank-Wolf method, and they are the same thing. Okay. So next topic is gradient projection method. So let's look at that method. So I'm standing at x naught. Okay, and I'm looking at the gradient at fx naught. So the gradient is pointing outwards. So in gradient projection, the idea is I'm standing at x naught, I look at the gradient of fx naught, I take a step in this particular direction. So let's say this is my, I don't want to call it x, let me call this y0. Now I've gone outside the set, okay? What I want to do is project this y0 back into the set itself. So I'm going to find the point which is closest, point within this convex set that is closest to y0. So that turns out to be this point. And this would be my x1, or at least this would be my x bar 1, x bar 0. And then I can pick an appropriate alpha k and I can descend in this particular direction. So that's the idea of gradient projection method. So the idea here is it's okay if I am outside the set, if I take a step outside the set, as long as I project myself back into the set and then take a step in that particular direction. So this is the gradient part, this is the projection part, and that's why the name is gradient projection method. Okay, so the way we define, so now we need to define what a projection means. So you have a point y, this is the notation for showing that I'm projecting y onto the set. This is argmin x in capital X, y minus x. So I'm looking at a point in the set capital X which has the minimum distance with y. Okay, so if I pick a point x which is in the set, the projection is the point itself, x itself, right? Because now that's the closest point within the set. But if I'm outside the set, then the closest point is of course different, and I need to be able to find the closest point. So the algorithm here, and I'll talk about projection in the next class, but I'll give you the algorithm today. So I have x bar k, xk minus sk gradient fxk plus and then xk plus 1 So you have two step sizes here. One is a smaller step size sk and the other one is a step size alpha k. That's projection. So I'm projecting whatever is the stuff inside, I'm projecting it back onto the set in order to get x bar k, and then I'm taking a direction, step size in that particular direction. Okay, so this is my y, and this is my projection onto the set. So this is the notation for projection. Can someone tell me what the difference between conditional gradient and this method is? So conditional gradient method, we have a linear objective function and we have optimization over a convex set. And sometimes this optimization could be easy, sometimes this optimization could be difficult, depending on the way the set capital X is defined. On the other hand, in this particular problem, I'm not solving this optimization problem, but I am solving this optimization problem. Okay? And depending on the situation, and we'll talk about projection in the next class, depending on the situation, sometimes projection is very easy to do, and we'll probably try to use this algorithm because projection is easy to use. On the other hand, in some cases, this problem is easier to solve, and therefore this is the problem, this is the algorithm we'll pick to solve the problem. So whenever solving linear optimization problem over a convex set is easy, we'll pick this algorithm. Whenever projection is easy, we'll pick this algorithm. Okay? And there are situations where neither projection is easy nor solving this optimization problem is easy, so we'll look at algorithms of that type in the subsequent classes. Typically speaking, the sets that are of this type, Ax equals to B, Cx less than equal to D. If you have a set of this type where the C and D are very high dimensional objects, then doing projection and doing this optimization, both of them are very complex operations. So we don't want to use those algorithms. So we'll come up with manifold sub-optimization method to solve problems of this type. Okay? So we'll look at it in the subsequent classes. Thank you so much. Next class, projection theorem, and complete this step, and then we'll talk about manifold sub-optimization method. Thank you.